Hello, I'm Laura Marshall.
And I'm James Lowe, and this is Light Matters for July 23, 2014.
On this week's show, a drone aids photographic lighting, a sensor diagnoses diabetes, fluorescence detects Alzheimer's, and a sensor amplifies molecular signatures.
A small autonomous helicopter can direct lighting just where a photographer needs it. Researchers at MIT and Cornell University developed a drone system to respond to the movements of a photographer and a photo subject using LiDAR and input from the photographer's camera. With the new system, the photographer can indicate the direction from which the rim lighting should come and the desired width of the rim, and the drone positions itself accordingly relative to the subject. The researchers will present their system at the International Symposium on Computational Aesthetics and Graphics, Visualization and Imaging next month in France.
A new microchip detects fluorescent signatures of antibodies associated with type 1 diabetes and could aid in prevention and early intervention. Created by a team from the Stanford University School of Medicine, a gold plasmonic microchip provides near-infrared fluorescence-enhanced detection of islet cell-targeting autoantibodies in blood samples. Glass plates form the base of each microchip and are coated with gold nanoparticles that intensify the fluorescence signal and enable more reliable antibody detection. The device can also distinguish between type 1 and type 2 diabetes, both of which traditionally have been characterized by blood sugar levels. More efficient testing has become crucial in recent years. Traditional categorization of those diagnosed with diabetes is no longer as clear-cut as it once was, thanks to changes in adults' lifestyles and factors such as childhood obesity. The microchip is inexpensive to manufacture and quick to produce results. There is no radioactivity involved, and the method uses less blood than traditional testing. The research was published in Nature Medicine.
Two fluorescence imaging approaches can now find traces of plaque associated with Alzheimer's disease in the eye, presenting possible opportunities for early intervention. Neurovision Imaging of California reports that preliminary results from 40 patients have shown beta amyloid levels imaged in the retina were significantly correlated with such levels in the brain that appeared during PET scanning. This imaging test differentiated between Alzheimer's and non-Alzheimer's subjects with 100% sensitivity and 80.6% specificity. Additional testing on patients in Western Australia is expected to be complete by the end of this year. Current methods to detect brain amyloids are invasive, expensive, and not conducive to repeated tests, according to the Neurovision developers. Meanwhile, Cognoptics of Massachusetts has used fluorescent ligand eye scanning to detect beta amyloid in the lens of the eye. The technique involves a laser scanner and a topically applied ointment that binds to amyloid. In its study, the company was able to differentiate Alzheimer's patients with a sensitivity of 85% and a specificity of 95%. The findings were presented last week at the Alzheimer's Association International Conference in Copenhagen.
A new spectroscopy technique can accurately identify the structure and composition of individual molecules. Researchers from the Rice University Laboratory for Nanophotonics developed a sensor that they say has the ability to amplify the optical signatures of single molecules by about 100 billion times. It is designed to study individual molecules that contain fewer than 20 atoms. The sensor uses coherent anti-Stokes-Raman spectroscopy, or CARS, in conjunction with an optical quadrumer amplifier made from gold nanodiscs. The researchers call the new method surface-enhanced CARS, or CCARS. The optical amplifier contains 4 nanodiscs in a diamond-shaped arrangement. Molecules' optical signatures are caught in a 15-nanometer gap in the center and can be amplified through the efficient light harvesting and signal scattering properties of the structure. Potential applications that could benefit from CCARS include chemical and biological sensing as well as metamaterials research. The research was published in Nature Communications.
That's it for this edition of Light Matters.
Email us your questions or comments at lightmatters@photonics.com, and don't forget to follow us on Facebook and Twitter for news updates every day.
Thanks for joining us. We'll see you again next time.